Okay, well, welcome everybody, and my name is Jeff Bodycomb. I'll be talking to you today about an introduction to laser diffraction, really for particle analysis. I'll pull in my last PitCon blurb, booth 1039, across the top. And then you can see the blurb-free title, Introduction to Laser Diffraction. So let me start by zooming out a little bit and showing this graph of particle size across the top, and you're going really in microns from about 1 nanometer up to about 1 millimeter. And you can see the names of the various size ranges. Nano-sized particles and colloidal particles all below about half a micron or so. Fine particles from about half a micron up to 10 microns. And then coarse particles from 10 microns up to a full millimeter. So applications you can think about for the nanoparticles and macromolecules, which would include things like polymers and proteins. And as you get bigger, suspensions and slurries, and finally on up through your powders. Now, how does all this fit in? Well, if you're thinking about analyzing your particles, you need a rough idea of the size to decide what methods will be applicable. So laser diffraction, which I'll discuss today, goes from about 10 nanometers up to several millimeters. If you want to reach the smaller sizes, you'll start looking at something like an electron microscope, shown in gray, or dynamic light scattering, shown in blue below laser diffraction. As you get to larger size particles, your options also change. You can look at optical microscopy, either the PSA 300 or the CAM sizer from HORIBA, where you take pictures of particles and get you can also extract shape information. Laser diffraction is a bit entertaining for a few reasons. One, it's been around a long time, and so there's a nice history to it. Second, the technique is extremely fast, and so you can really get data much more quickly than almost any other sizing technique. And third, the size range is very wide, and so it really spans the range of several other techniques, and so that makes it tempting, particularly if you expect your needs will shift in the future. The core principle in laser diffraction is you can use light to look at the particle and extract its particle size. So I have this cartoon where I have a light source on the left shining onto some particles, and I look at it in different angles. I find out the particle size distribution. Now the rest is getting into useful details. And we'll start with what happens when light strikes a particle. Well, some of the light is diffracted. That is, it's kind of be absorbed or irradiated by the particle. We'll just call it absorption re-irradiation, which is somewhat different than the absorption re-irradiation here, which is more thermal. Refracted, where the particle acts like a lens, or reflected, where the particle acts like a mirror. If you want to figure out what's happening when light strikes a particle, you need to know about the optical properties of the particle. The real refractive index, which is how light is bent in the particle, or the wavelength of light in the particle. The imaginary refractive index, absorption of light within the particle. I'll throw in the comment that refractive index values become less significant for large particles and for small particles. It's the ones in the middle that get you. And light generally should be collected over a fairly large range of angles, not just the forward angles, but also around to the back angles. So here is a graphic with the LA960, which is the HORIBA flagship particle size, laser diffraction particle size analyzer. You have a laser on the right going through a lens, and then you have your particles in the flow cell in the middle here, and you have scattering in all directions. And you'll see a ring detector, which is a clever way to extract scattering at very narrow forward angles in the front, along with a series of wide-angle detectors to measure the scattering as a function of angle over a wide range of angles. In addition, we have a blue light source, and I'll talk about why we do that later on, which again is used to excite generally the wider angle detectors. So what So now that we've kind of seen the optical arrangement, what are we trying to look at? Well, we're trying to get what's known as a diffraction pattern. You shine a beam of light onto an object, and you look at the scattering. Generally look at, so if you project this on a screen, you might see a very strong beam in the middle. That's the light beam just continuing on. And then you'll see rings and various spots as you move further and further away from the center. And these rings and spots depend on the size and shape of the particle. Well, why would this tend to happen? Well, what is light? Light is really an oscillating electric field and an oscillating magnetic field that's orthogonal to electric field. So I have this cool cartoon in the bottom right where I have the electric field oscillating up and down, the perpendicular magnetic field oscillating back and forth, and that's really what's happening with light. And all sorts of interesting things happen when you add up oscillating functions. So if you have oscillating electric field and you add it to a second electric field with some sort of phase shift, so that's kind of like taking the red and the blue and you add them together. If there's almost no difference in the phase, the amplitudes add and you have a bigger electric field amplitude or brighter light. So the intensity of light goes by the square of electric field amplitude. If the fields are out of phase, then as you start to add them, they will cancel and you'll have a very weak intensity. Okay? And so it's this interference concept that gives us these scattering phenomena. Well, why would we have a path length, a phase shift? Imagine I have a giant particle here and I have light coming from the left side of the screen, and then at some point in the particle I have scattering, and at another point I have scattering from another spot in the particle. Well, if I put my detector at the bottom right corner, so it's far away, the distance from this lower point to my detector is different from the distance from the upper point to the detector. So I will add these two oscillating fields and find out, hey, I have a stronger intensity. Now if I put my detector in a somewhat different spot and I add these two fields, I will get a weaker intensity. So depending on where I have my detector, I will get different intensities for scattering from these 2 points. And you can start adding this up over all the points in your particle. Now, I said that scattering is dependent on particle size and shape. Typically, scattering data cannot be inverted to find particle shape, and that's because in most real particle samples, the particles are somewhat different shapes, and so you will obtain some sort of average. The second is that the particles that you're measuring are tumbling. So I'll just go ahead and warn you of that in advance. The second is that what we do is we go and we use optical models to interpret the data and understand our experiments. So it turns out to be a fairly manageable problem to go from a particle size and figure out the scattering pattern, but somewhat less manageable to get from a scattering pattern and go back to a particle size. So we just calculate the pattern for every possible size, see what fits. So if I wanted to go and calculate the scattering pattern for every possible size, how would I approach that? Well, if you're working with fairly large particles and you don't have a lot of computer time, then you'll use a Fraunhofer Approximation. Math is nice and straightforward. I'll show you that in a bit. You're really modeling the particle as large opaque particles and they're two-dimensional disks. Still a great way, in my opinion, to develop your intuition for scattering phenomena. I like it a lot for that. But with a modern computer, there is no reason to use it in practice. A much more general approach is Mie scattering. The calculations are very messy, and you do need a computer, and it takes even a noticeable amount of time on a computer to make the calculations. The particles, the model is valid really for all particle sizes and treats the particles as three-dimensional spheres. So we have the Mie model, which is three-dimensional, which actually tells you about what's happening inside, or thinks about what's happening inside the particle, and the Fraunhofer, which treats it as two-dimensional and doesn't really think about what is happening inside the particle. So here's the easy one, Fraunhofer. The scattering is going to be proportional to incident intensity, a few other factors, where most important one is this alpha, which is diameter divided by wavelength. I'm just going to tell you something about how you might design an instrument. And you see it's simply a Bessel function, or the square of a Bessel function. That's going to give you a hint about what Mie looks like if I'm telling you that this Bessel functions are the easy ones. The limits is that you really need a fairly large particle diameter for this to work. And it works out to usually about 25 microns or so that the Fraunhofer approximation starts giving decent results. So I make some plots of intensity on the left as a function of scattering angle. And the blue is a 50 micron particle, and the red is a 100 micron diameter particle. I make this a log-log plot in the bottom right because that is a bit easier to look at. And you see two things. Large particles scatter more strongly, first, and second, that the first order peak for large particles is a narrower scattering angle than for small particles. So it's kind of an opposite reciprocal relationship where big particles, small scattering angles. Another plot kind of giving you the same idea except with two-dimensional scattering plots. So these rings will be the scattering from a large particle where you have low angles and very strong scattering, and small particles with peaks at wider angles and a weaker scattering. So I've talked about kind of this regime, and we have a poll, if I can get this going, which is what particle sizes do you work with? Are they over 1 millimeter? Are they between 25 microns and 1 millimeter? Between 1 micron and 25 microns, and less than 1 micron. And so I've kind of already covered the case of 25 microns and up, which is the Fraunhofer. Although I'll point out and recommend that you go ahead and use Mie scattering even for these larger particles. It is certainly not going to hurt you and can help you in some edge cases. Okay, close. And the bulk of the audience, call it the modal value, has between 1 micron and 25 microns as their particle size range. So you're certainly in the right talk because this is the right instrument. And we'll talk a bit about how that case is handled. So this is Mie scattering. I have another webinar I give every so often on advanced laser diffraction where I briefly mention where this comes from. So the scatter intensity is much more complicated. It really comes from the sum of these S1 and S2 values, and those are sums of functions of Riccati-Bessel functions. And so what I want to draw your attention to are really the three important variables: the scattering angle theta, the value of m, and the value of x. Okay. The rest of this is math. It's actually these are fairly difficult numerical problems. Still some active work on the best way to approach them, generally around how to calculate them quickly. So the equations are messy, but we only need three inputs. X, which is pi d over lambda, and you remember that from Fraunhofer. So what that tells me is if I want to look at small particles, if d goes down, if I can bring lambda down at the same time, I could do pretty well for making a good measurement. That tells us why we have a blue light in the LA 960. We also have m, which is a relative refractive index, and that's going to be the refractive index of the particle divided by the refractive index of the matrix, or the material around the particle. And finally, we have theta, or the scattering angle, and that depends on the geometry of the instrument. Now, I kind of blew through the equations without going into much detail because the, how to say this, the machine does it all for you. And so there's some mathematicians back in Japan who worry about this on a pretty regular basis. We don't have to, so that's a good thing. When you start using Mie, you will certainly stumble across the need to know the particle refractive index, and then you'll be asked for the real part and the imaginary part. So the particle refractive index tells the math how light behaves inside of the particle. The real part is going to be the change in wavelength of the light in the particle compared to air, really, or vacuum. And the imaginary part is going to be the absorption in the particle, or how the intensity of light decreases as you travel through the particle. Now, we use complex numbers because it actually makes the math easier. If you are adding and subtracting a bunch of cosines, using complex numbers makes life easy. So that's why we talk about it as the real and imaginary refractive index. Here's a quick comment on the short wavelengths for the smallest particles. This is a plot of scattered intensity on the left as a function of scattering angle. And I'll normalize these so they both have the same max intensity. And if I used a red light source, the variation from 0 degree scattering angle to 180 degree scattering angle is only 11%. But if I go to a blue light source, now this variation intensity is about 25%. And so there are two lessons in this plot. The first is you get a lot more signal when you use blue light. And notice that really your signal in a scattering measurement is how much does scattering change as a function of angle. If the scattering does not change with angle, you know nothing about your sample except the particles are too small. If it changes a lot and has lots of peaks and valleys, you can extract quite a bit of information. And so this big 25% change is something nice and meaty to get your hands on and figure out what is happening. The second is it tells you need the background stable to within about 1% of the scattered signal to measure small particles accurately. I should go back and comment, this is why the LA960 is so heavy, because the design philosophy was make it rigid as all get out, and that involved more metal. And so this plot tells you why the thing is so hard to pick up. Well, you throw in a blue laser, you add more metal, what do you get? You get nice results for size distribution on the left as a function of particle diameter for 30, 40, 50, and 70 nanometer latex standards. So we're pretty happy about that, and it also works for other materials. Incidentally, when I use Mie scattering and I look at scatter intensity as a function of scattering angle, I see exactly the same trends that I saw with Fraunhofer. Large particles, small angles, and strong scattered intensity. I am also allowed to extend the calculation all the way out to 180 degrees scattering angle and down to quite small. Well, I'd extend it to 1 micron particles. Here it gets, a fellow would get silly to keep going, but you can keep going as long as you want. Those of you who have been working in particles for a while realize that nearly every real sample is a mixture of different particle sizes. So how do we treat that? Well, we just add. So if you have the scatter intensity from 1 micron particles in the green, and then you have some 2 micron particles mixed in the black, I can just add up these two scattering patterns and get a weighted sum according to how much of each to find the scattering pattern that I measure for that particular mixture, which is shown in the blue. And you can see how some of the peaks at the 2 micron diameter have been suppressed because I have the valleys from the 1 micron particles. Quick comparison of Fraunhofer versus Mie. Works quite nicely at 100 microns and for angles up to about, let's call it 1.5 degrees or so. If I go to 10 micron particles, the initial peak position might be okay on a good day if you're not looking very closely, but the match is not very good at all. Does this matter? Absolutely. If you're using glass beads and you expect a size of, well, the neighborhood of 15 microns, is actually they're 13 micron beads, and you measure them and you treat with a Fraunhofer kernel, which is shown in blue, you obtain a D50 of about 4 microns and 2 peaks in your size distribution. Fraunhofer just can't deal with some of the lensing effects of glass at all, even at 10 microns. So this is a pretty big difference. The LA960 and the HORIBA software does support Fraunhofer calculations. So you can do it if you want, and we do, but I tend not to want to. As I move down in size, if I have a CMP slurry for polishing wafers, for making computer chips and the like, then I expect sizes in the nanometer range. But if I treat my data with Fraunhofer, I might see a size of 1, 2, 3, 4 microns in blue rather than the expected 150 nanometers in red. Again, big difference. If you see 4 microns, you're going to panic and shut everything down to figure out what went wrong. Okay. Well, you noticed I mentioned before that we can calculate the scattering from individual particle size, and then we just add it up to figure out the scattering pattern from a mixture of particles. So how do we take a scattering pattern that we measure and find the particle size distribution? All the methods come down, there are various numerical approaches. They all kind of come down to the same sorts of questions. You start with the initial scattering pattern. You calculate a size distribution. You say, okay, well, and then you calculate the scattering pattern from this size distribution and see how well it matches your initial measurement. As you can expect, the initial match is not so good, so you have some difference. And you'll use that difference to calculate a modified distribution and then recalculate your scattering pattern from that second iteration of distribution, compare, check the difference, and so you'll go back and forth estimating a new size distribution and then going back and seeing if that new size distribution is closer to your original measurements. So, some other factors in the measurements is that size, shape, and optical properties also affect the angle intensity of scattered light. So there are some effects due to the shape of the particles. And it can be extremely difficult to extract shape information without a priori knowledge. So we need to assume a spherical model for the particles. If you were to align all of your particles, and if you were to have a two-dimensional detector, and if you were to have particles that were all a fairly uniform shape, you might get a little further than that. But generally, through most of life, using a spherical model is what you need, and that's the most efficient way to extract information. So now I have a quiz. What particle shape is used for laser diffraction patterns? So you only get to pick one. Okay, I think I'm going to go ahead and close this. Share the results. So I have 46% hard sphere, 46% easy sphere, and 7% cube. Now I got to admit that hard sphere and easy sphere score equally. They're both, I'm going to take them both as correct. And someone did ask me, what is the difference between hard sphere and easy sphere? And that's just me kind of goofing around. Okay, so we'll hide that.
They must be new to our audience, Jeff. They're not used to your humor yet.
No, they just had no way to express. They had no way to ask what's going on.
Right.
Okay. Okay, I did get a question in, which is how often should these machines be calibrated? I'm going to go into a bit about instrument-to-instrument measurements in the next section. By calibration, we're really going to be confirming instrument operation with standards. And so you're going to go find yourself some particle size standards, preferably polydisperse, and make some measurements and see if the results match what you expect from the bottle. That's kind of a risk-based decision. Some quick checks are fairly inexpensive. I've seen pharma outfits that will confirm their instrument performance before every critical measurement. Especially, I'm thinking of one case where they share the instrument with an R&D group, and they're clever enough to know that R&D doesn't always make the instrument, clean the instrument up perfectly before leaving the room, if you will. So anyway, so going back to that, it's risk-based. Instruments do not tend to drift over time. Generally, you're not going to see much change, and so you might want to stretch that out, particularly if you're in a less critical application. Some people have a service contract, and part of the PM we confirm instrument performance. Oops. Okay, so how do you make a measurement? Well, prepare the sample, and that is usually a significant fraction of the effort, because all this mathematics and the calculation I talked about before are handled within the instrument. And it's good to know what's happening, but it's not necessary during a day-to-day measurement. You want to use good sampling and good dispersion, and the instrument will reliably measure whatever particles you give it. So if you scoop off the top of a drum and the particles are systematically oversized because they've vibrated the top of the drum during shipping, you will get that answer. You may need to use a surfactant or something else in order to ensure the particles are in suspension. You need to prepare the system. Align the laser to maximize signal to noise and acquire a blank and a background really to subtract off. This is simply done with the press of a button in modern instruments. Okay, so you press a button, it aligns and blanks. You add the sample, and you hit measure. And so here's a screenshot that will kind of show you what's going on. On the left-hand side, you'll have some sort of graph giving you transmitted intensity through the material. You'll have a pump running around. You'll add material until this transmitted intensity is in the right range. By the way, in this particular example, someone added way too much. Then you'll hit you might use some ultrasonic to break up the particles, and then you go ahead and hit the measure button. Samples can arrive in different forms and in different quantities. So fraction cells requires about 10 ml of liquid. Paste cells, well, I guess what it sounds like, it's for paste. The mini flow is for 35 ml or so of liquid dispersion, and the auto sampler lets you, well, run multiple samples. And keep in mind, you can run these samples also as dry powders. So if your starting material is a dry powder, then that might be the most convenient way to go. Okay, I did get a question. Why is the blue transmission area larger, generally larger than the red? See if my, okay, so good, this example shows that. Well, this bar drops with absorption, and generally blue light is absorbed more strongly than red light. And so that's why you'll often see that trend. How much sample do we need? Well, it depends on the sample. So if I could use about 1 mg of a biopolymer, if I'm using a fraction cell, and that's 100, yeah, so that's 1 milligram material. As I move to larger sampling systems or to smaller particles, I will need more material. So colloidal silica wanted 132 milligrams, and that was not a fraction cell, I suspect. Mag stearate, 0.16 milligrams, and notice the particle size is about 10 microns, and that may have been the fraction cell. So really come ask our applications lab. It's going to be sample dependent. It can range from milligrams up to hundreds of milligrams. If you're running dry, well, we had 2 guys in our lab get themselves into a little competition about whose method was better, and that evolved. I'm not sure which way it went, but it got into this thing about, well, I can do it this way, I can get to this mass, and we actually pushed the measurement down to a little bit less than 5 milligrams for a number of different particle sizes. And so anyway, that's what particle sizing people do for fun in Irvine. Measurement workflow, click measure, hardware measures distribution, the software then calculates the size distribution. If you look in the software, you can actually see the scatter intensity as a function of channel, as well as the final result of differential size distribution as a function of diameter, or cumulative size distributions. Well, there are a lot of different switches you can turn in your sample preparation. There's circulation pump speed, which is how fast you move the sample through the system. The particle concentration, how much do you add? How much ultrasound do you add? And how long do you make your measurement for? So really, as you develop a method, if you're going to be measuring something for QA, you'll want a fairly robust method, and you'll systematically vary pump speed, particle concentration, ultrasound, and to a lesser extent measurement duration to figure out which of these parameters are important and what values are most appropriate for your sample. We do have a wizard that helps support those kinds of experiments. So what it really does is it'll guide you through to say, okay, make a test, and then we will plot your size distribution as a function of, in this case, refractive index used for calculation. And you can decide which result makes the most sense. For refractive index, you often look at R parameter. Reproducibility, that's very important, and that's going to come up particularly in method development. And so one thing you look at is you vary things like air pressure for measuring dry powder is how reproducible is the result. And so this is magnesium stearate. We ran it 1, 2, 3, 4 times, mean size of 4.58, a standard deviation of 0.01 microns, coefficient of variation of 0.2 microns. So we were all pretty happy about that. Got to D50, that was D10, sorry, D50 was standard coefficient of variation of 0.3, and D90, coefficient of variation of 0.9%. So again, very nice overlay of the curves, pretty pleased with the result. And that's one of the great things about laser diffraction is that you can get really nice reproducible results. And so when you see a change in results, you really know that something has happened to your particle system. Cement is interesting material, very important to things like roads and buildings and a lot of modern technology, although it's been around for an awfully long time. And so particle size turns out to be pretty important, and it has a sizes that range from a few microns up to tens of microns. So here's some measures of Portland cement dry with D50s of 11 microns, D10 of 3 micron, D90 of almost 25 microns, and coefficient of variation about 0.24% on D50, 2.6% on D10, and 0.7% on D90. So if I can measure cement dry, how about measuring it wet and seeing if I get the same answer? So that's what we did. We measured it in isopropanol. We felt that adding cement and water to our expensive analyzer would not be a great way to enhance our particle analysis careers. It turns out if you're really quick, you can do it, but I don't recommend it as a routine thing. Anyway, so we have cement and IPA, because that's just a lot less stressful. D50 11.7 microns, coefficient of variation 0.8. So zip back, 11.1 micron, 11.7 micron, very nice match. D10 of 2 microns wet, 3 microns dry. Well, one nice thing about the wet dispersions is the liquid will coat the surface much better than air will, and so we get a smaller value for D10. But again, they're still very close, makes us feel very good about both wet and dry measurement, and the person who is interested in measuring cement may want to decide whether their cement is arriving as an already dry material, and it's easiest just to dump it into the hopper and go, or if it's arriving it's kind of damp, they might put it in IPA and make the measurement. Instrument to instrument variation. So here we are talking about running polydisperse standards on 20 different instruments. So PS202 from 3 to 30 microns up to a standard that's 500 to 2,000 microns. Now polydisperse standards are interesting for a couple of reasons. The first is they obviously check how accurate your optics are, and you will also do that with monodisperse standards, those with very sharp size distribution. But the wider size distribution means that your pumping and dispersion procedure to separate the particles also has to be good. Because if your biggest particles are settling because your pump is not working properly, you're going to see shifts in your results with these polydisperse size standards. Anyway, across 20 instruments and 5 standards, the coefficients of variations of 1 to 3%. So, and the worst was on D10 for the largest size standard. And most of them were 1 to 2%. Pretty happy about that. We have some customers who use multiple instruments at multiple sites, and so they do their own internal checks, and we were able to share some information. So this is formulation 1 and formulation 2. So we don't know what exactly was being measured. We do know that the mean size across 4 sites and 4 instruments had a coefficient of variation of 0.5% for the first formulation and 0.8% for a second formulation. So we're pretty happy about that similarity. And then if we look at D50, again, very low coefficients of variation. Very nice repeatable results, and it means that you can compare the 2 results from 2 different sites using laser diffraction results. Another fun application is pigment hiding powder. Well, one thing is you go to grind, and somebody who registered for this expressed an interest in inks, and this is the one application I could dig up in a hurry last night, so I thought it'd be fun to add. You'll grind a pigment, and then you'll measure the hiding power. And by you, I really mean you, because I don't think I could do this all by myself. You know, the material is spread onto a paper, and an expert looks at it and says, okay, well, this has a hiding power of whatever, okay, as a percentage. You need to wait for the material to dry, and you need someone who knows what they're doing to look at these ink swatch. I suppose they're pigment swatches. You can also measure size distribution throughout the grinding process, and that's shown in the bottom here. So here I have the grinding time on the bottom and the hiding power on the bottom axis, bottom left axis, and geometric mean size on the top left axis. So as the geometric mean size goes down, then with time you also can see the hiding power go up. And so you might decide, hey, I'm going to grind to a target geometric mean size because that's a lot easier to explain to my operators than try to grind to a particular hiding power target. So that's something you can do with laser diffraction, where you can take these grinding results and discuss them in the terms that make a lot of sense to the operators and directly something they can go work with to make a better product. Whereas if you discussed in terms of hiding power, people may get a little confused. Okay, what are some drawbacks of laser diffraction? Well, the first is it's a volume basis by default. That works out pretty well for mass balances, but you really can't calculate number basis size distributions from laser diffraction without pretty significant errors or uncertainties in your results. And that gets truer as your particle size gets down and as your distribution gets broader. The second concern about laser diffraction is that you don't have any shape information. So if you dump a sample into a laser diffraction instrument, you're going to get a nice repeatable size distribution, but you won't know anything about particle shape. And that is interesting for some applications. So what are the benefits of laser diffraction? Wide size range. The advanced analyzers can go from 10 nanometers to 5 millimeters. What that means is when you invest in a laser diffraction instrument, you're kind of future-proofing yourself. As your customer needs change, you can change with them. Flexible sample handlers. Again, the same thing. You can work with powders, suspensions, emulsions, pastes, creams, and so you can do all sorts of different kinds of work. It's very fast, gets you very high throughput, hundreds of samples a day, and so if you want a lot of data, and often that is useful, you can get it with laser diffraction. It's easy to use. I like to disappear into the weeds about how measurements are made and dealt with. A lot of this intelligence is built into the machine, and so you have fairly automatic software and self-guided software. You can create sequence files that will just tell an operator, here, just press this button and you're done, and they will get a reliable result. If you have good design, then you'll get excellent precision, and that means less time for extra investigation and downtime. It's a first principle measurement with no calibration necessary. Really, laser diffraction relies on knowing the wavelength of your light source and relies on the geometry of the instrument. Neither one is going to change under normal circumstances. And of course, if you replace the light source, that's going to be a little different. Or if you take a Sawzall to the instrument, could change some angles. But there's no real calibration necessary. So when you run standards to check, and going back to the question earlier today about calibration and how often, you're really checking to see if everything is still working properly. Okay, you're not putting in a particle sample and adjusting some switch to get the right answer like you would with a pH mirror. There's a massive global install base in history. There's a lot of information about how to optimize a technique. There's a lot of information about how different processes deal with the technique and so on. And it's some pretty neat science. Turn all these red. Okay, I'm going to open the discussion, or leave the discussion open, I guess is the best way to put it. In case you want to ask a question, go ahead and ask it into the chat box. Keep reading our monthly newsletters. You can visit our download center to find video and slides from this webinar. We are slowly catching up on that score. www.horiba.com/us/particle. And you can find me at jeff.bodycomb@horiba.com.